now with this, let's try and figure out how to realize the filter. We will go proceed exactly in the same way as we did with the first order prototype. So, this is Vi, this is Vo. Okay. So, this is nothing but I. So, I is nothing but I of s is nothing but Vi minus Vo by R plus SL, which basically means that R times I of s is nothing but Vi minus Vo divided by 1 plus SL by R. And once I is known, Vo is nothing but 1 over Sc times I of s, correct. So, if I multiply by R and divide by R, Vo of s is nothing but I of s times IR of s times 1 over SCL. Okay. So, now if IR, if I call this Vx of s, all right, what do we do? Well, let us assume Vx of s is here. To generate Vo, what will we do? You integrate it. So, we already know how to make a voltage in, voltage output integrator. This is R and C. So, this is going to give us minus Vo of s, correct. But then what we need is Vi plus minus Vo by 1 plus SL by R, correct. So, what do we need to do? We need to add Vi with minus Vo. Vx, to get Vx, what do we need to do? We have, let us assume that we have obviously have Vi, we have minus Vo. What do we need to do? We need to add the two and process the, and to generate, I mean, what is this? What is this transfer function 1 by 1 plus SL by R? It is a first order low pass filter. We already know how to build that low pass filter. And what is the DC gain of that low pass filter? 1. And what is the omega naught of that low pass filter? R by L, correct. So, I mean, but we already know how to find. So, how do we add these two? How do we add Vi with V naught and then low pass filter the combination? Pardon? We already know how to make a low pass filter, right. So, this is the low pass filter. This has got a gain of, if you call this R and you call this R and you call this C, this is a low pass filter with a, this is, what is the transfer function from input to output? Minus 1 by 1 plus S R C, okay. And but what do we want? We want transfer function 1 by 1 plus S L by R So, how should we choose this RC here? Now, do you understand what I am saying? So, basically if you choose C to be equal to L by R square, then you will have the transfer function from here to here will be 1 by 1 plus SL by R, correct. Okay, but the transfer function we have is minus 1 by 1 plus SL by R. Okay, so this is Vi, and to this we must add minus V naught. So, what should we do? To generate Vx, we need to add Vi with minus V naught and then filter low pass filter that result, correct. The low pass filter is here as shown on the left, correct. Now, this is only going to filter Vi with 1 by, I mean it is going to filter Vi with this transfer function. We have, we have two problems. One, of course, is the sign is not correct, right, and the other one is it only filters one input. So, we want to filter Vi with minus V naught. So, what should we do? Add another parallel branch. Very good. Where? In parallel with Vi, you basically say, okay, here is another resistor. What must be there here? Minus Vo. Okay, if we do this, this output is going to be minus V naught plus Vi by 1 plus SL by R, correct. I mean we are going to get the negative. So, we want to get we want to invert the output. So, what should we do? So, the simplest thing you can do is put an inverting amplifier. So, this is R. What should we do now? What is the result? Vi minus the signal here is nothing but Vi minus V naught by 1 plus SL by R, which is the same as what? Huh? It is the same as Vx of s. And if you integrate Vx of s, you will get minus V naught, right. So, basically you short these two. So, this is our Vx of s, this is minus V naught, and this is minus V naught, this is minus V naught. So, what should we do? Connect the two. So, okay. So, this basically gives us the second order low pass filter, right. Does that make sense? And I mean we wanted Vo of s, but what we are getting is minus Vo of s. So, it is an inverting low pass filter, right. And so, the transfer function Vo of s by Vi of s is nothing but 1 over 1 plus s square 1 plus SRC plus s square LC. Okay, where this capacitance, if we call this C1, must be chosen as L by R square, this is C2. So, which is nothing but 1 by 1 plus S what happens here? SR C1 or C2? C2, okay, plus S square R square C1 all right, it must be minus. That makes sense. All right, we have simply implemented the equations that basically govern the passive network, just like we did with the first order case, right. There also we did the same thing, except that now you have a more, I mean you need an extra integrator, because you have two integrators here, right. The inductor is integrating voltage and converting it into a current, right, and the capacitor is integrating a current and converting it into a voltage. So, you need two integrators, and therefore, you can see that there are two integrators in the active RC prototype, right. And what comment can we make about loading now? The loading will have no consequence, because the output impedance is 0, right. And what comment can we make about stake capacitances? So, every node you can see is either a virtual ground or the output of an op amp, right. So, stake capacitances do not have, right. Now, let me quickly let us stare at the circuit and get some intuition. Let us say this is the first time you have ever seen this circuit. Okay. So, and they ask you what is the DC gain of the circuit. How will you figure it out? At DC, all the capacitors are open. This is what it is. Okay. So, how do we know that there's negative feedback around all the op amps? Yeah, we break the loop. So, the last, let us do it for the last op amp. So, let us say we break the loop here, and we yank this side up. What happens if that goes up? What comment can you make about this node? Goes down. If this goes down, what happens here? Goes up. If that goes up, what happens? Goes up. So, there is indeed DC negative feedback around this op amp, and you can do that for all the op amps and check it out, right. So, so that is one thing. So, the virtual grounds of all the op amps are 0. So, at DC all the current DC current flows there. So, where will all that DC current flow? Through which resistor? Why? Last op amp, what is the current flowing here? 0. If this current flowing is here is 0, this voltage must be 0. If that voltage is 0, what is this voltage? 0. If this voltage is 0, what is this current? 0. That is why all the current flows to that resistor and not the other one. right. So, all this current flows, so this is Vi by R. So, the voltage here must be minus V. So, the DC gain is 1 and is negative. Is that clear? Okay. So, this is basically what you should see at DC. Okay. Now, so this is what C1 is it? This is, and this was C2. At very high frequency, the capacitor is a short, right. So, what comment can you make about at high frequency, this capacitance is a short, this capacitance is also a short, a very low impedance. So, what comment can you make about the output voltage? Is approximately 0. So, and this voltage is 0. So, what comment can you make about this voltage? 0. So, this voltage is also going to be 0. So, what comment can you make about this current? Through which impedance will it flow? Why? Why? There is no capacitance, there is no potential difference across C1, there is no potential difference across R, there is no potential difference across this R also. I mean, this voltage is almost 0, this voltage is also almost 0. So, among R and C1, if current flows, both of them have the same voltage across them, through which will current flow? Through C1. Now, now compared to C1 and this R, through which will more current flow? Through C1, right. Okay. So, basically the voltage here, therefore, at high frequency, this voltage is going to be approximately, the current is V by R, the impedance is 1 by SC1 and it is inverting. So, basically SCR1, correct. So, this is an inverting amplifier. So, what will be the voltage here? Vi by SCR1. So, now what will be the voltage here, therefore, at high frequency? Vi by SCR1 times the transfer function of the integrator at high frequency, which is minus 1 over SC2, I mean C1R, SC1R, yeah, C2R. So, basically this will be approximate high frequency, this will be minus Vi by S square C1 C2 R square, correct, which also comes out from the expression. So, as you can see from here, at high frequency it must be S square R square C1 C2, which is basically the same as what you see, right. Asymptotically, I mean, when you look at a circuit at very high frequency and at very low frequency, you should simply be able to look at the circuit and then figure out what the asymptotic response must be without actually calculating the entire transfer function and putting S equal to infinity or 0. You understand, right. I mean, for example, if somebody asks you, if you look at this network and asks you what the response is at DC, what will you do? You will open the capacitor and short the inductor. You will not find the transfer function and then put S equal to 0, right, because you are only interested in the response at 0 and you should not have to work so hard to find the entire transfer function and then put S equals 0. Is that clear? Okay. All right. So, we will stop here, we will continue in the next.